like pH diagrams. They tell you so much about what's happening in the system at any point. Where, the state of matter, the value of temperatures, enthalpy, volume, entropy, and all how they all relate to each other. So if I can actually switch the slide. There we go. So in this masterclass, we're going to be talking about what else we can do with pH diagrams and talking around those concepts and then translating them to real world examples. So in this, we're going to be looking at how pressure drops affect the vapor compression cycle. We're going to look at how subcooling and superheat look on a pH chart and what their real world effects then would be. We're going to look at the line of compression and how it differs between ideal compression and non-ideal compression. And then we're going to look at, say, how efficient real-world compressors actually are. We are then finally going to look at varying condensing and evaporating temperatures and what effects they have both on the pH diagram and in the real world. So firstly, pressure drops. Pressure drops are present in every single system. Some pressure drops might be very low, some might be very high. But from the discharge valve of the compressor until the suction valve of the same compressor, the refrigerant is always undergoing a reduction in pressure. So when discussing pressure drops, we need to talk about flow a little bit, not a massive amount, but a little bit. There are, in the main, two types of flow. We have laminar flow. It is simply a uniform flow through a pipe with little to no mixing between layers of flow, and it has a low pressure drop per meter. See, sorry, let me get the laser pointer up. And here, everything's moving in the same direction. We're not changing much. And then we have turbulent flow. And turbulent flow is, well, turbulent. It's chaotic. It's defined by mixing, and it has a high pressure drop per meter in comparison to laminar flow. And to be frank, we need both. Laminar for efficient fluid transport, such as through liquid lines and through suction lines, and we need turbulent for efficient heat exchange, really. So let's just have a look at the pH diagram, or in itself, what is actually termed the log pH diagram. So if we have a look, everything on the log pH diagram, I've snipped a little bit here for reasons, but all the red isotherms, these lines of constant temperature, they're relatively evenly distributed. And that's great for an A4 landscape sheet of a pH chart. But pressure axis changes. So for the same distance, from 0.5 bar to 1 bar, we cover this distance, and then same distance, we have a 1 bar difference, and then a 2 bar, and we have a doubling. And that's effectively why it's called a log pH chart. And that is very good for keeping things on one A4 sheet of paper. But if you're asking what the so what is, then you're in good company. The so what effectively means that for an identical pressure drop measured in kilopascals or bar, effectively has much more of a effect at lower pressures than it does at higher pressures. And we'll just have a look at this now. I'll convert an absolute pressure drop to an equivalent drop in saturated temperature. Why do we do this? It's because temperature is what drives heat transfer. Systems control on pressure, but refrigeration and heating happens with temperature differences. So if we have a 0.5 pressure drop on a R4FA system, a minus 10 degrees evaporating and 40 degrees condensing, we can see our discharge, our drop in saturated pressure, temperature for the discharge would be 1.1 Kelvin, and we use Kelvin for temperature differences because rather than degrees C, or certainly I do. And liquid slightly higher, 1.16, but the suction is 3.5 Kelvin. And that's all for the same absolute pressure drop of 0.5 bar. Now, this is important because, as anybody who's heard me speaking, I will bang on about this rule of thumb that for every 1 Kelvin change in saturated suction temperature, it affects the COP by 2 to 4%. and and it's very similar for the saturated discharge temperature. And the point to remember as here is that pressure drops have a greater impact at lower pressures. So here's a cycle showing a 2K pressure drop, a 2K drop in saturated temperature on the suction, a 1K drop in saturated temperature on the discharge, and effectively a 1K drop in saturated liquid pressure. Yeah, but just note the sizes. Obviously, we have a 2K pressure drop here, but it's disproportionately greater than, say, the discharge pressure drop. We can also note that we've got slight slants here, where we have included for a 40K pressure drop on the condenser and a 7 kPa pressure drop on the evaporator. Now, what I'm trying to show here is that whilst all pressure drops are important to some degree or another, the most important pressure drops that you should really be accounting for in your pH diagrams is your suction pressure drop and your discharge pressure drop. And then to a lesser extent, until we get onto subcooling, is your liquid pressure drop. And like I said, just to reiterate, the reason why we express pressure drops in terms of saturated temperature changes is because these are much more useful in being able to ascertain the effect on heat transfer and cycle efficiency than an absolute pressure drop that changes with pressure, refrigerant density, and so on and so forth.